Hello everyone, welcome to our EVE 302 project presentation. I'm Sirean, and together with my teammates Sonny and Sarah, we've been investigating sedimentation processes for removing microplastics from water. Today we'll demonstrate how particle characteristics and coagulants affect sedimentation rates, which is crucial for designing effective water treatment processes. We'll show you our experimental setup, results, and analyze how they align with theoretical predictions based on Stokes Law. As for the problem statement, microplastic pollution has become a global issue affecting our water systems. These tiny particles, less than 5 millimeters in size, have infiltrated virtually every water source on Earth. Conventional water treatment systems aren't specifically designed to remove these particles, which can be harmful to aquatic ecosystems and potentially human health. Our project addresses this need by examining sedimentation as a cost-effective, scalable solution for microplastic removal. In our previous submittals, we identified flocculation sedimentation as an economical approach compared to more complex technologies like reverse osmosis or specialized filtration systems. Today's demonstration will show how these principles work in practice.
Our experiment was divided into two phases. Phase 1 was density testing, and Phase 2 was sedimentation modeling. Phase 1 had us using a graduated cylinder and scale to get more accurate information about particle density and size so that we could refine our model for the particles we were using. This is followed up by Phase 2, where we set up our mock sedimentation tanks, I'll talk about that in a minute, to get a real-world measurement of settling distance and time. Going into a little more detail about our sedimentation modeling, we started by filling 8 half-liter water bottles with 400 milliliters of water. We then added 12 grams of salt to each of these bottles so that we could observe sedimentation in a saltwater scenario, this matching the approximate concentration of 30 grams of salt per liter of water. These bottles were then paired up into 4 sets, which were going to be matched with each of our sediments, those being coffee beans, plastic beads, plastic sequins, and sand. We added 5 grams of each kind of sediment to each of the pairs, and then we flipped these bottles over and calculated the distance fallen and the time it took to fall. These values were used to then get our real-world velocity and compared to our predicted values. Before we look at our experiment, it's important to understand what variables changed and why we changed them. Our 3 independent variables for this experiment were particle density, particle size, and the presence of a coagulant, which in this case was sodium chloride. Particle size and particle density are both key terms in Stokes' settling equation, so they were natural choices for our independent variable. Although it is important to note that there is a link between these two variables in our experiment. This is because we were changing our material type, which meant that whenever one changed, the other had to change with it. Our last variable was also the presence of a coagulant. Coagulants are often paired with sedimentation in real-world water treatment, so we wanted to see if that would affect things in our experiment. This is just a quick look at our fully set up sedimentation tanks before we ran the experiment. Here you can see the video taken during our experiments. I wanted to point out some key things we saw. Obviously, each of these particles settled at different rates. We ranked these in that table here. The sequins are an interesting case where some settled and some didn't. This is likely due to their high diameter and low density, making them more affected by internal forces and currents than the other particles. Despite their large diameter, the coffee beans did not settle. They had a very low density, which implies that density is the more important of the 2 factors we tested. Sand and plastic both have higher densities than water, and they settled like normal, which was unsurprising. It's also important to note that the coagulant had no effect, likely due to the fact that we were using inorganic particles, which made the sodium chloride ineffective, and the fact that our organic particle, the coffee beans, were just too large to coagulate.
As for our results between particle properties and settling behavior, let's look at the data we collected. According to our measurements, when we compared these observed settling velocities with our theoretical predictions using Stokes' Law, we found some interesting discrepancies. For example, our equation predicted sand would settle at 0.07 centimeters per second, but we observed a rate of 0.95 centimeters per second. These differences highlight important real-world factors that affect sedimentation beyond the idealized conditions of Stokes' Law.
Our project was based on Stokes' Law, which describes particle settling based on size, density, and fluid viscosity. We model sedimentation, a key step in water treatment, using a simple bottle setup. The diagram shows where sedimentation fits in real systems. The test was simple and low cost. Results showed density and size affect settling as predicted by Stokes' Law. Sodium chloride had little effect, likely because it doesn't help aggregate inorganic particles like litter. Still, our setup showed basic systems can support microplastic removal. Reflecting on the project, we found density had more impact than size, though some results didn't match theory, showing the limits of simplified models. Next time, we test common water treatment coagulants like aluminum or ferric chloride since sodium chloride wasn't effective with our particles. We'd also use smaller particles, improve settling measurements, and test temperature effects. These changes would make the system more accurate and realistic. This is the end. Thank you for listening, and we hope you enjoyed our video.